Made out of wood. All right, oh good. Well, it's about start time here, so I want to jump right into here. I told you this was a big chapter, and sure enough, it is. In fact, I kind of want to split it into two, and so the first half I've already talked about. I'll kind of review here real quick, and maybe even add a little bit, but now I want to do some examples. And so I know normally these first 8 chapters, what I've done is waited till the end and then did some examples. But I think this chapter deserves a little different take on it. It deserves a chance to pause halfway through, and really it's more than halfway. It's more like 2/3 of the way through. It's the majority of it, and there's not really that much more to do. But it's 2 basic ideas, and so what I want to do is a bunch of examples. So that's probably where we'll spend the majority of the day, and then we'll get a little bit into the rest of the lecture, and then on Monday kind of finish up the rest of the chapter and the rest of the examples, and then go on to chapter 10. So if I review what we did so far, the idea was this. And the important principle here is this conservation of momentum. And it's worth saying again that what I hope you get out of this class this semester is that I'm really just trying to teach 6 basic concepts. Newton's 3 laws of motion, and then the 3 conservational principles. The same 6 I kept telling you in Physics 102, and I'm telling you again. Of course, now it's at a calculus level, and you're beginning to see how you're taking your calculus, or your Math 150, together with those basic principles of physics from 102, and putting them together, and with a lot of details, we got some very analytical type of problems. And you definitely saw that in these last homeworks we've done, as well as the test, and you'll see that again here as we move forward. But here was this idea of conservation of momentum, and that was if you had an object, so let's call this cart number 1, maybe it will have a mass 1 and it will have some initial speed, and it makes contact with car number 2. So let me call it mass 2, let me call it initial velocity of number 2, and I'll say they're going in the same direction. But when I write out the equation, please know that could be a negative number, so it could be going the other way. And obviously, if they're going to collide, number 1's got to catch up to number 2. It's got to, obviously, number 1 then has to have a greater speed than number 2. But the idea was this, that we said the change in momentum of number 1 would be the net force on number 1 integrated over time, and that would be the change in momentum of number 1. And so if your focus is just on number 1, and that is if you draw a little dotted line, let me get a different color here, but if you draw a dotted line around this and you say, okay, that is your system, well, as cart 1 hits cart number 2, there is an outside force. And that is cart number 2 is pushing on cart number 1. And when there's an outside force, is there conservation of momentum? No, right. When do you have then conservation of momentum? Yeah, a closed system in the sense that there's no external forces acting on this system. And so that's why if we were to do the same type of arithmetic, and I guess these are vectors, so I'll put a little vector there. But if we were doing the same kind of, and I shouldn't even say arithmetic, but mathematics, calculus here, on cart number 2, then there would be a net force on number 2, and number 2 would change its momentum. And the same story goes, that if I were to put a dotted line around cart number 2 would have an external force, that external force coming from cart number 1, and so cart number 2 would change its momentum. But together, and this was the key, together then, and maybe I'll go to yet another color here, but together, if I group these 2 together so that force on number 1 comes from number 2, and force on number 2 comes from number 1. And without repeating the lecture we did on Monday, hopefully then you will notice then that because there is no other forces, the net force on 1 is equal and opposite to the net force on 2. And the 2 then, of course, when added together, give you a net force of 0. Or simply put then, when 1 gains momentum, like the case number 2 might gain it, number 1 loses it. And so there is no net change in momentum of our system. And that was the key here. And that's what I want to do with some examples here, is look at some different scenarios. Look at them maybe individually or collectively as a system. And when we have a system with no external forces, then our momentum is unchanged. And so when you write out the equations, what you're really saying then is something like this. The initial momentum is equal to the final momentum. Now, of course, in more detail, what that means is the initial momentum of number 1 plus the initial momentum of number 2 must equal the final momentum of number 1 plus the final momentum of number 2. And then if we write that in more detail, that means mass 1 times velocity of number 1 initial, and I should even say vector, mass 2 times velocity number 2 initial must equal then mass 1 times the final velocity of number 1 and mass 2 times the final velocity of number 2. Okay? And so that's the basic equation. Now, if we also add to this, and this is what I was trying to emphasize at the end of the lecture then on Monday, that not only is there conservation of momentum, that is, if we don't have external forces, which we would in this case, but we also have conservation of energy. So that means the initial kinetic energy must equal the final kinetic energy plus maybe any heat that is created during the contact as number 1 collides into number 2. In fact, we even used some fancy word. If no heat was created, what kind of collision did we call that? Elastic. If some heat is created, what do we call it? Inelastic. If they collided in such a way that they stick together, we called it perfectly inelastic. So watch those words as you're doing the homework there. But nonetheless, we're just going to think about Q. Sometimes Q will be 0, elastic. Sometimes it'll be not 0, inelastic. Sometimes the two will stick together so that the final velocities are the same, and we'll just call that perfectly inelastic. And so there's some fancy words that as you read them, make sure you don't miss them so that you know what you're doing. Are you putting in 0 here or non-zero? Are you putting in same speed or not same speed? And so there's the idea. Now if I write this out in more detail, this would be 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. And so that would be the initial kinetic energies as I put the two together. And then that's got to equal 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared plus any heat that might have been created in that process. And that's pretty much where we left off. What I didn't do, and probably should have rushed it and finished it up on Monday, but I go, well, this will be the first thing I do on today, Wednesday, before we get into some examples, is this is all a scalar, so there's really nothing more I can do here. But what I didn't show you is, doesn't this have vectors? So doesn't this have x components and y components? And so really my description so far has been the simple case where we just have a one-dimensional motion. That is, this is an m1 v1 initial x plus m2 v2 initial x must equal m1 v1 final x plus m2 v2 final x. But please remember then, since these are vectors here, this could have a y component, And so if the objects can move in a two-dimensional pattern, then this really represents two equations, the equation for the x and the equation for the y. And so I'll write that out in detail here, but this would be my equation in the y direction. And a picture may look something like this, that instead of having some carts, maybe I'll have a hockey puck here. And so I've got this little puck, and the puck is sliding along. And again, I picked the hockey one for really two reasons. Number one, it's played on ice, so the friction, we can say, is zero. Okay, so very little friction anyways. And number two, they don't tend to rotate that much. Whereas if this was a game of billiards, then there's the rotation to the ball. And we haven't done any rotations yet. Although that's soon to come. That's where chapter 10 starts off, and so we can deal with that. And the rotation and the interaction of the rotation with the felt is going to make it a more complicated problem. So I didn't want to get into that quite yet. But, or I'm kind of thinking of that, what's that game? Shuffleboard, thank you. Yeah, where you try to hit the discs together. So you got that smooth concrete and they slide across, which, I don't know, that's probably about it. Hockey's probably more common than that one. Either one, we just don't have much of it here. We don't have any ice. And none of you are senior citizens, so you probably don't play the shuffleboard there. But the idea here is if two things collide like this, without a rotation, and this could be, maybe a better example might be two cars. Because we do have a lot of accidents there on our busy streets there. And so two cars come together and slide, although they're not really frictionless either. But it may look something like this, and then the second one may kind of ricochet off like that or something. You know, depends on the problem. And I'm kind of drawing this one as if the second one is kind of stationary at first. And so you know, like that shuffleboard problem. You've got one disc coming in and it hits another disc, and you know, it ricochets off, and then the two go off at an angle there. But my point being here is that if it does go off at some angle, then we've got, you know, this two-dimensional type of problem. We have to conserve momentum in the x and conserve momentum in the y. And then we have conservation of energy. So simply put, the principle, I don't think, is overwhelmingly difficult. It is, hey, momentum is conserved. Momentum before equals momentum after. But please remember, it gives you two equations. It gives you an x component and y components. You put that together with the energy, and we have a total of three equations here. So we've got momentum conserved x and y. We've got energy conserved there. And they've got a lot of terms in there. So given the fact that we have three equations, we could really solve for three unknowns, right? And so a problem, you know, could start off something like this and say, you know, here is the initial velocities, here is the mass, it hits it, and maybe they tell you the angle of this one, but not the angle of that one. So I'll call one theta, one phi. And then we would have some final speed for number one. We would have some final speed for number two. But if they gave us one angle, but not the second angle and not the two speeds, don't I have three equations and then three unknowns? If they've given me everything else, like they say it's an elastic collision. So if they tell me it's elastic collision, they've given me the Q, they haven't given me the final speeds, they have given me the initial speeds, they haven't given me the angle of one of them, but they've given me the other. And so three equations, three unknowns. Now, I must admit, not an easy set of three equations, three unknowns. One has squares in it, the other doesn't. And so it can be kind of a long algebraic problem, but that's kind of the key to this. And so use conservation of energy and momentum together with all the other stuff we learned, and you'll see how the problems fall together.
The heat created by both pucks or just one of them?
Well, how do I answer one or both? It's both. It's during the collision. So the heat that I'm talking about is the heat of the impact when the two come together. And so when these two come together, these molecules are going to push on those molecules, just like these molecules are going to push on those. So you hit, and all of a sudden these molecules start going faster, and these molecules start going faster. So there's heat created in the collision. There could also be an energy of deformation. If these were two metal bumpers on a car, it would take energy to change the bonding angle of all those metals. But the energy goes somewhere. If it's not just heat, it is in the deformation of the metal. And goes somewhere. But the point I do want to emphasize is I am not talking about a heat due to a friction of these sliding on the ground, right? Because if they were sliding on the ground and there was some friction, would I even have conservation of momentum? No. So we got to be careful with conservation of momentum. We've got to stop and make sure we have a system with no external forces. In fact, one of the last examples I want to do today really illustrates that. Well, as I said, I think the kind of the best approach is to actually just do some examples at this point. Even though there's more to the chapter, this is such a powerful tool in and of itself right here, and I don't want to lose the information or the moment, and I want to do these, and this will give you the tools to at least do half, if not more than half, of the homework this weekend for chapter 9, and then we'll look at the next half of the chapter, which has to do with center of mass. And so for the first time we'll give our object size, and so you can begin to see that I have objects now that have size. This is the shape of a triangle, this is two balls here, this is half circle type thing. This is a fun one to look at too, and so we'll kind of look at the next half of this chapter, if, like I said, when and if we get that far here. So as my first example, let's do number 14. And I picked this one not because it's hard. You'll see that it's, you know, and what is your author? He does make it a blue problem. Not that it's hard mathematically is what I mean to say, but it's just a new way of looking things. And that's what I want you to see. It'll also help you, by the way, with one that is very hard, that in the past I've had students ask me a lot about. It's number 69. And so you might want to make a note in your notes here that if you are struggling with number 69, come back and look at this example, number 14. Not quite the same, and I would admit 69 is a little harder than this one, but it sets the stage for something you might overlook the first time you do it here. Watch, let me read it again. The first time here it says, water falls without splashing at a rate of 0.25 liters per second from a height of 2.6 meters into a 0.75 kilogram bucket that sits on a scale. If the bucket was originally empty, what does the scale read 3 seconds after water started accumulating in it? Okay, so like I said in all these, first step is that physical picture. So looks like what I have is a bucket. Okay, the bucket itself is 0.75 kilograms, and water is being poured into it from a height of 2.6 meters, if I caught that right. Yeah, 2.6 meters. Now, it's flowing down or flowing into the bucket at a rate of 0.25 liters every second. So here's the water. Now it says the bucket starts empty and is sitting on a scale. Now, after a given period of time, of course, the bucket's now going to have some water in it. And it does say after 3 seconds. So we start with an empty bucket at time equals to 0. And I wonder if they mean time equals to 0 when the water starts falling, or 0 when the first little bit of water hits the bucket. Let's see. And I think they made it clear. if the bucket is originally empty, what does the scale read 3 seconds after water starts accumulating in it? So I read that as time is 0 when that first little water hits the bottom of the bucket. Okay, that's what it says to me. So I could figure out how much time it takes for that water to fall down. And I think are going to need that. Maybe not before this is done. But that's not what they mean by that. They mean 3 seconds water has been accumulating in the bucket. All right. But here's the real key to this. This is why I picked this one to get started, because it's very easy to overlook one thing about this. If I go ahead and I draw a free body diagram of the bucket. Here's the bucket. Here it is filled with water. Well, let me do like I did over there. Let me put a dotted line around my system. And I could even ask this, are there external forces on this? Yeah. So this really isn't a conservation of momentum problem yet. That's about to come here. But what I do want you to see here is the things pushing from the outside would be this normal force coming from the scale, right? In fact, that's what the scale reads. The scale reads how much is it pushing up. Okay? Now, what's pulling down on it? Well, would you agree there would be the weight of the bucket and the weight of the water? Okay. Anything else, though? Right, and that's what's new here. I want to make sure you didn't miss that. That what is happening here is the force from the water, although in this case I'll think of it in terms of the change in momentum of the water, and so maybe I'll call this force number 1 there. Okay. And so as I add up my forces in the vertical direction, I would have the normal pushing up. I would have then an M1G pushing down, an M2G pushing down, and the reason I picked this problem was for that new piece. The momentum, the impact that the water, as it comes down, makes into the bucket. And so all of this should add up to be 0 since the whole bucket is not accelerating. But I did want you to catch, and it looks like most of you did, that the reading on the scale is not just the weight of the water and the bucket, but also the impact force. And so that's what I wanted you to get. And so recognize that when you do number 69 on the homework. That one has a chain, and you're holding the chain up here. And the chain is just barely touching the ground or table, and it gets let go. And so the chain is falling. And they say it falls some distance x. Well, if it falls some distance x, that means you have x amount of chain on the table. But the question is, how much force is the table pushing on the chain? It's not just the weight of the chain that's on the table. That's certainly part of it. But the other part is the fact that each link is coming down and making an impact. And that's what's new here. And so I want to make sure you got that piece. Because these two pieces, I think you can handle. This isn't that tough. This is the weight of the bucket. So that's just 0.75 kilograms times 9.8 meters per second squared. So that's the weight of the bucket. That's the simpler one. Now, the weight of the water maybe is a little bit harder, but certainly not overwhelming. I mean, how much water would I have in the bucket after 3 seconds? Yeah, so after 3 seconds here, I should have 0.75 liters. Now, does anybody know how much a liter's mass is? Yeah, it's 1 kilogram here. So don't I also then have 3/4 of a kilogram of water? So there is the mass of the water. So you got to know about the density of water, that it's 1 kilogram in 1 liter, or 1 gram in 1 cubic centimeter, however you want to look at it. But that takes a little more work. But again, I don't think that's the hard stuff. Here's the hard stuff then. How do we do this third piece? How do we calculate the force? Yeah, and so this is how we are looking at the force, right? How the momentum is changing with time. Okay? And so it comes back to this derivation, which came from Newton's second law, that force equals to ma, but when we rearrange that, we put it together to say how the momentum is changing with time. And so coming over to here, looking at how the momentum changes, if I were to just maybe draw a dotted line across the opening of my bucket here, I guess, well, maybe I should make it right where it splashes. And I know it doesn't happen instantaneously, but it's probably a short period of time where the water flowing in has some momentum, hits, has a force on it, and now has no momentum. I know it's probably a little more complicated than that with the water swirling around. But overall, then, it has no more momentum going in the forward direction. Maybe it's swirling around here, but if some's going left, some's going to the right. The whole thing's not moving left or right or up or down here. So that's this idea that there would be a change in the momentum, and that might be a little bit hard to see because momentum is mass times velocity. Watch this step. dm dt times v plus m dv dt. I mean, what'd I do there? Right, I just took a derivative with the product rule, right? But be careful how you look at this, because our view is a little different. What I'm viewing is a line across here, and I'm viewing the water as it is flowing by this line. Now that's different than anything we've done in the past. In the past, we've viewed the object like here, a chunk of mass moving down. And as it moved down, didn't we view the mass as unchanging? And so in the past, I would have said my dm dt is 0. In the past, I would have said, look, the mass doesn't change. What changes is the velocity of the object. And so I would have mass times acceleration. But now in this view, I've got both terms. Now it turns out that this term is 0 and not this one. And so that's our new view here. So looking closely at this, here's what I would say. Look at the rate at which the velocity is changing. Now again, imagine yourself standing right here where the water hits the bucket, the bottom of the waterfall. As it is flowing in, wouldn't you say that the speed of all the water flowing in is the same? So is there any change in speed? No. Not when viewed in that way. The change in speed would occur in another view. That is, if you were riding along down the waterfall, if you were the guy in the barrel going over Niagara Falls, then you'd be changing your speed. And then you would hit the bottom, and then you would change your speed. Okay? And so this term would be very important to you in that view. But as a view of the tourist, the bottom of the waterfall, looking at it, you're just saying all that water is coming in at the same speed. And because of that, you would say this term is 0. And this dm dt is what? It's the rate at which the mass is flowing into the bucket. And so this is the 0.25 kilograms every second. Okay, And so that's what I wanted you to see. And then that, like I said, will help you in this view, will help you with that couple of the homework problems where you want to take a look at that. Now, of course, I still have this question about, well, what is the speed of the water? But that really goes back a chapter to conservation of energy. And so let's figure out what the speed of the water would be when it got here. And so I could say, well, mgy initial is its initial potential energy, and 1/2 mv final squared is what happens to that energy when it gets down here. So going back to our conservation of energy, and that was my warning for you. Don't forget about this new stuff in momentum, but as you're doing it, remember to use your old stuff. And so this is really saying that the speed then would be 2 times g times the height times the square root. And so this would be 0.25 kilograms per second times the square root of 2 times 9.8 meters per second squared times 2.6 meters. And so that is that term. And so, as I work these out, we now have our answer. And I'll do this one first. 0.75 times 9.8. And so that is 7.35 newtons. And the other one is 7.35 newtons. So weight of the bucket, weight of the water. The added piece is the force needed to stop the water as it is coming down this waterfall. So I'll get the speed first. I'll go 2 times 9.8 times 2.6. Take the square root of all of that. And so that's a speed of about a 7. And times 0.25 gives me a total of about 1.78 newtons. I thought it was more than that. Did I hit anything wrong? 2, 9.8, 2.6. That's 50, square root of that's 7. Okay. So there's the extra added piece that can easily get overlooked. So 7.35 twice, and then the answer from the last one is about a 16.5. So the reading on the scale should be about 16.5. It is not only the weight of the water and the weight of the bucket, but also what we call that impact force of the momentum of the water coming in. And like I said, wanted to make sure I grabbed that one so you saw it. So there's the first example. Let's try another one. How about number 22? 22 illustrates this idea, I think, pretty good, of the momentum and conservation of momentum, and is it conserved or is it not conserved, depending on whether there is internal forces only or there are some external forces. Let's read 22. 22 says a 7-gram bullet. I'll stop right there. 7-gram bullet. What are they trying to do to me? Yeah, watch your units here, right? I know a number of times I don't always put in the units because they always work out for your base units, but they start mixing around newtons and and grams, you're going to run into troubles here. So go back to that chapter 1 there and be real careful with your units here. All right, so I lost it. 22. 7-gram bullet. It is fired from a gun into a 1-kilogram block of wood held in a vise. It penetrates the block to 8 centimeters. This block of wood is now placed on a frictionless surface, and a second 7-gram bullet is fired into the block of wood. To what depth does this bullet penetrate? Whoa. Did you catch the problem? I mean, let's study this carefully here. Again, good physical picture so we don't write down the wrong things. It's really talking about 2 different steps. The first one here is to take this object, and it's held in a vise here. It's got some kind of clamp here, maybe I'll put it on a table of some type here like this, but maybe a C-clamp comes around here, and you know, we go through here. But the idea is we are going to clamp that 1 kilogram block into place. We fire a 7-gram bullet at it, so the block can't move. It penetrates 8 centimeters inside. So that's the first description. Block of wood, clamped real tight with a vise, can't move. Fire this bullet at it, goes inside, 8 centimeters. Now I hope you caught in here that the whole idea of the vise was to say there's some kind of external forces on here, right? Is momentum conserved in this process? No. Now of course that also depends on what do you mean by your system, but if I look at the bullet by itself, is the momentum conserved for the bullet? No, obviously the bullet slows down. Okay, how about the bullet and the block system, the two together? No, because there's still external forces on it. There's this clamp. This clamp comes from the table, and the table's hitting the earth. So I suppose if you said, how about the bullet, the block, the clamp, and the earth system? Is it conserved there? Yes. Okay, yes. But not going that big, just with the bullet and the block, looking at it as my system, I don't have conservation of momentum. The bullet is clearly moving. A little bit later, now the bullet and the block still aren't moving. But where it changes is in part 2. Part 2 says, let's do this all again. Let's take this block, which I suppose you may argue is now more than 1 kilogram because it's got a bullet lodged inside of it. So I'll add the extra weight. But I have a feeling that's why the author gave such a small mass to the bullet and a large one to the block to say, look, that's not really what I'm after. I'm not after the fact that it weighs a little bit more. Okay, but let's just say it's 7 grams more now. But the second firing here is another bullet, so another 7-gram bullet, and it's going to fire into here, and it's going to get embedded in here. How far does it go? Does it go 8 centimeters? No, new hole. New hole. Yeah.
You added to the mass a little bit? Is that how it happened?
Well, I did add to the mass, but let's say I didn't add to the mass. Would it go just as far? It won't go as deep. Why not?
Because it's allowed to move.
Right, it's allowed to move here. So something that was rigid, it's going to put a force and come to a stop. Something that can move, now you push on it and it moves back. And so it can move with you. And it's going to be a lot less force on it now. It's going to go a lot less. I mean, it's like asking, can you punch your fist through a piece of paper?
No.
You might be surprised. I mean, if you hold up a piece of paper, and I put my fist through it. See, I'm not even strong enough to push through a piece of paper, right? Now, if someone were to hold it here, then my fist could easily go through there. But there's a different effect if the thing can move and give back a little bit. And that's what you're seeing here. And so we're going to hopefully see here that this bullet does not go 8 centimeters. I'm not sure what it goes. Does it go 7? 5? 2? Who knows? But how am I going to answer that? Well, let me ask you this. Now that we've removed the clamp, and it's just sitting on this table, and it says that it's on a smooth, frictionless table, do I have conservation of momentum for the second one? Yeah, I do. And that's going to be the key to this. Well, when you say it's negotiable, are you saying that the author's a liar and may not be right? But I think he makes it very clear. So I would say no, it's not negotiable. It says the block is then placed on a frictionless horizontal surface. Okay, so now how you make it, I don't know. We'll put Teflon on Teflon here and let it slide across there, okay? But assuming that, I mean, that's the given part of the problem. But here's what I wanted you to see in this. If I then draw a dotted line that includes the bullet and the block, because there's no friction, the only forces involved here are the forces that the bullet puts on the block and the block puts on the bullet. And so if I include those two objects as my system, there's now no external forces and momentum is conserved. So how would I apply my equations to scenario 1 versus scenario 2? Well, let's try scenario 1. First of all, you already told me. Do I have conservation of momentum for scenario 1? No. So I'm not even going to talk about the equation for momentum for scenario 1. But do I have conservation of energy in scenario 1? Yeah, most definitely. So I would have this. I would have 1/2 mv squared, where m, little m, is the mass of the bullet. And so I'll use capital M for the mass of the block. And then I'll use little v for the velocity of the bullet. And same thing down here in scenario 2. Although in scenario 1, I don't need a capital V, but in scenario 2, I do. Doesn't the block now move? All right, so I'll need a capital V for scenario 2. But going back up to scenario 1, this would be the total kinetic energy. And where does all that kinetic energy go? Yeah, it's clamped, it's held in place. The whole idea here is you're not going to have any kinetic energy. It's all going to go into heat. I'll call it a Q, but you might even call it force times distance, where the force is the friction as the bullet penetrates in there. And then D is the distance it travels, which we are told is 8 centimeters. Okay? And so that is what scenario 1 tells me, using the principle of conservation of energy, but I can't use the principle of conservation of momentum for that case. But as I jump down into scenario 2, as you said, do I have conservation of momentum? Yes. So I would write this as mv, so little m, little v. Isn't that the total momentum before the collision? Equals what then? Yeah, now that the bullet is lodged inside, I would have little m plus big M times the v that they're now moving. And so this is where they stick together. So we had a fancy name for that. What was that? Perfectly inelastic. So this is a perfectly inelastic collision. They didn't use that word, but the perfectly inelastic means that the two are stuck together and have the same speed. So that's what this means. Same speed, total mass is now the two of them added together. Don't I also have conservation of energy here? All right, so let me write that out. That would be 1/2 mv squared. Just like before, that's the kinetic energy before the impact. Where does it go? Okay, good. We've got a 1/2 and the mass times the speed squared. In other words, they're moving, so there is some kinetic energy. But then there's also heat created there. And so maybe I'll put that as force times distance, and I'll put a d prime here, indicating that that's what I'm looking for. That's the point of this problem. What is the depth that this bullet penetrates now? Will it still be the 8? And as we argue, no, it should be less. And you can kind of see that here in terms of the momentum, in terms of the mass. And so let's put all these things together. let's take this information from this scenario, and let's take these two pieces of information from this scenario, and I claim that we can figure out then what is d prime from all of this. But I do want you to see how I solved it with conservation of momentum and the older stuff, conservation of energy. Yeah.
So you just use a different V for notation?
A different V? Oh, so this is supposed to be a capital V. Because, I don't know, would it be better if I did 1 and 2?
No,
Yeah, I'm just, okay. So this is the V after the collision. This is the V of the bullet before the collision. But watch what happens if I use this equation together with this information. See this term right there? Can't I just say it's force times the distance of the 8 centimeters? That's what this is here. If I take that and substitute it in. Equals what? Well, this is my 1/2 little m plus big M. And now let me use the momentum step up here. Couldn't I solve this one for capital V? And put it into here? So I'm going to put this into here, and I'm going to put this into there. And so that would be a little m squared, a little v squared, over an m plus a big M squared. And so that's what happens when I move that to that side of the equation. And then plus force times the d prime. And let me take a close look at this. You will notice that one of them upstairs cancels with the one downstairs. But if you look at that 1/2 of v squared and one of the m's, isn't that what this is here? So in other words, if I put one of the m's and the m plus big M, capital M, I leave those alone, this other part is 1/2 mv squared, which is force times distance from scenario 1. Now, again, if I kind of remember back to chapter 5, as the bullet is penetrating through here, what kind of friction is this? It's a kinetic friction, right? And what was nice about kinetic friction is, wasn't it the same value regardless of how fast or slow it was going? So as this bullet comes in and it's going very fast and then slow, the force was the same. That's why the energy was just force times distance. It was just the integral. And the force didn't vary, so we didn't have to do an integral. It was just force times distance. But it's also why I could say that even though this one is now moving backwards as it is being struck by the bullet, the force of friction is still the same. And so this force and this force and this force are really all the same. And so I can cancel those off. And so I get D equals m over little m plus a big M times d plus d prime. So there it is. That's what these three pieces of information work out to be. Conservation of energy here, conservation of momentum and conservation of energy here. Take the equations, put them together, and I can solve this for d. So d prime now becomes the d minus little m over big M times d. So this d is 8 centimeters minus, and the mass is 0.007 in terms of kilograms. And when you add the two together, you're 1.014 times the 8 centimeters. And so I have 8 centimeters minus, it's not much, so it's not going to be that much different. 0.007 divided by 1.014 times the 8, and it's 0.055 centimeters. That small? Okay. I thought it would be a little bigger than that. But I guess they gave me a pretty heavy block. And so even though it's not clamped with a vise, it's still going to be pretty sluggish to make it move. It's just got a lot of mass compared to the bullet. Okay, so it doesn't go quite as deep. But hopefully it illustrates my point and what I was trying to say here. It's kind of amazing how many different types of scenario and problems we can do by making sure we write out both principles, and then if we have different scenarios, both principles if they exist, but in this case just one principle. But here's our energy principle, our energy with our momentum principle, and manipulate around the information, and we'll get things like how far does it go. I'll try 25. 25 is another one kind of similar to this. And you'll want to ask yourself, right at the beginning, is this momentum conserved? And if it is, great. I know energy is conserved, so I'll use that too. But put that information together, maybe even with a free body diagram and forces and work and kinetic energy. And so we've gotten to the point in this semester where we've got a lot of pieces now. That first test was all just kinematics, just who we knew it was, acceleration, velocity, and the decisions on what to do and how to do it were a lot easier than they are now. Because now we go, God, do I do it by forces? Do it by energy? I mean, how do I work it up? Yeah.
Do you have any extra packets with you by any chance on track?
Oh, I do have a bunch of extra packets. At the end of class, I'll get them. But if you need one in the homework packet, yeah. So I know some of you picked it up in the test, some of you picked it up in the lab, but yeah. But definitely get working on these this weekend. Yeah, at least half this chapter, the ones involving the momentum. Well, look at 25. 25 says a 12-gram wad of sticky clay is hurled horizontally at a 100-gram wooden block initially at rest on a horizontal surface. The clay sticks to the block. Oh, now that was a key word. Clay sticks to the block. What are they telling you? Perfectly inelastic collision, right. After the impact, the block slides 7.5 meters before coming to rest. If the coefficient of friction between the block and the surface is 0.65, what was the speed of the clay before the impact? Okay, well, again, like all these problems, pause for a moment, draw a picture, get a good scenario here of what's going on here. All right, so we've got this big wad of sticky clay, and I think they said its mass, 12 grams? Yeah, 12 grams of the sticky clay. Okay, so here is my 12 grams. Here's the clay. It's being hurled forward, and I'll call this velocity v. I don't know what it is. That's the question. What is this speed? And then it comes along and it hits a 100-gram block of wood that is sitting on a table that does have some friction. And again, they gave that coefficient of friction. They said that the coefficient of friction was 0.65. So there's actually quite a bit of friction here. So 0.65. And what happens is it pushes it. Maybe I'll give my table a little more room here. But they said on impact, the two move together. And so maybe this big wad of clay now is stuck on here. And they say that the thing slides 7.5 meters. Okay? So it comes along, makes impact, two stick together, slide across, 7.5 meters. Lots of friction involved. The question is, what's the speed immediately before the impact? All right, let me ask you a couple of questions, two in particular. Is energy conserved? Is momentum conserved?
No.
All right, the energy part, hopefully you say right away, yes. Energy is always conserved. Now, it doesn't always stay as kinetic energy, and in this case it doesn't, right? It's obviously got a lot of kinetic energy at first, so there's the clay. When it makes impact, doesn't some of that kinetic energy get converted into heat? So, right upon impact, I would say that these molecules in the clay, these molecules in the wood, they get pretty warm. And so this is our perfectly inelastic collision. But that's not all that happens. Now that it starts to slide, it slides across here. In other words, we still have some kinetic energy, but as it's sliding, what's happening to that kinetic energy? Yeah, it's going into heat. So these molecules down here begin to get warm, and I guess these molecules along the 7.5 meter path of the table start to get warm. And eventually it comes to a stop. So doesn't all the kinetic energy eventually end up as heat? But it's at different places at different times. So keep that in mind as we start to work that out. So, is energy conserved? Yes. Does it all remain as kinetic? No. Does any go to gravitational potential energy? No. Does any go to spring? No. It all goes to heat. Some at the impact, some then later on by the friction sliding along. But a bigger question is momentum conserved?
Given the friction.
Okay, I would say no, it's not conserved because we do have some friction. Except, and the reason I picked this problem, is if I look at this scenario, and I would say there's some friction here, I would say as it goes along, there's less momentum, less momentum. In fact, wouldn't you agree that by the time it got here, how much momentum does it have? 0. And didn't it have some before? So yeah, there's clear evidence that the momentum wasn't conserved. Except, be careful with these problems. That's why I picked this as a good example. What about the instant of the impact? In other words, right after, before there starts to be all this friction. And so what I'm going to say there is, we could apply conservation of momentum at that point. In other words, the momentum right after impact is the same momentum as before impact. Now, if it starts to slide 1 meter, no, then it's lost some momentum. And by the time it has slid 7.5 meters, it's lost all of its momentum. And so take advantage of that little instantaneous scenario that, hey, we haven't really had any friction yet. There's no sliding going on here. And so right before versus right after. Okay? Because when I say the momentum before, and I put mv, and I set it equal to m plus capital MV, what I am really saying here is little m being the mass of the clay, big M being the mass of the block, capital V then is the velocity of the block right after impact. And so I would say this is true, but only right after impact. Because then, as you are correctly getting from this, is as it slides, this V gets less and less and less and less. And in fact, that's how I want to do my conservation of energy here. If I call this Q1, the heat that's created during the impact, and I call this Q2, the heat that is created while it is sliding, if I look at the whole picture, I would say 1/2 mv squared is the kinetic energy before the impact. Where does that energy go? Well, some of it goes to the heat created upon impact. Some of it goes to the heat as it was sliding along. But if I break those into two pieces, then I would have 1/2 mv squared equals 1/2, and then I can add the two masses together and say this is the speed right after the impact, so this is the kinetic energy right after the impact, plus the Q1, right? And then as I monitor it as it goes across the table, this would be the kinetic energy that it has after the impact. It goes to Q2. Does that kind of make sense? And so I've got the what happens at impact and then what happens for those few moments as it slides across the table. And so this is immediately after impact. This is kind of looking at the whole thing. This is looking right at impact, that we still have some kinetic energy. And this is looking at the sliding part. This is saying, hey, this is the kinetic energy you have. Where does it all go? It goes to heat as it is sliding along. The reason I say that is I don't think all of these are going to be really important for this problem. Now, they could be important for other problems. That's why I wanted to mention it and make sure you put all your pieces together, because that's the difficulty of any physics problem, any word problem, any real world problem is, you know, how do you begin? Where do you go with this? And I wish it was easy as just giving you a recipe, you know. You want to make chocolate chip cookies? Here's what you do. You get out the recipe book, you put in 1 cup of chocolate chips, you put in 1 cube of margarine, blah, 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 blah. You go through, you bake for 6 minutes, you got your chocolate chip cookies. It's not that simple when solving problems. It's like, how do you approach it? And different people approach it different ways, and different problems have to be approached in different ways. And you got to look at everything that's happening, think about all of your options, and decide what is going on here. And I'm suspecting that this one and this one, although are true, really aren't relevant. I'm not sure, so I'm going to just put a line through them, but a light line, so I can come back and look at them. Because what is going on in my mind is I know a lot about Q2, and I know very little about Q1. What do I know about Q2? Yeah, they've given me coefficient of friction. They've given me distance traveled. I mean, I bet I can get the normal force. I can get from that the frictional force. I can get that the distance. And from that I can get the heat. So I think I can get this one. And if I can get this one, then I can get the speed after the impact. And then if I can get the speed after the impact, I can get the initial speed before the impact. So it's these two that are going on in my mind of how I'm going to solve this puzzle and put those on. And completely pay no attention to the Q1, how much heat was created on impact. But of course the question could have asked that. There could have been part B, how much heat is created upon impact. Oh, okay, so then I better think about it. Okay. So let's look a little closer then, as you pointed out, with Q2, this heat that's created as it slides along here. It would be the coefficient, the frictional force times the distance it traveled. And that frictional force would be the coefficient of friction times the normal. Fortunately, they gave me an easy case for the normal. I'll draw a diagram if it helps, free body diagram, but I'm hoping you remember this simple one. What is the normal force for this guy? Yeah, this is just the weight of it, mg. Now, is the normal force always mg? No. So you don't want to fall in that trap. I warned you a lot about that in chapter 5. But in this case, the simplest case here, what we have is this is pushing up, which during the sliding, it would be, during the sliding, I'll call it the normal force, but the weight is the two together now that they've been combined together. And so that would be my free body diagram in the vertical direction. I guess to complete my free body diagram, I would have this frictional force. That's the part that's slowing it down. But I don't need the horizontal forces to get normal, because over here the sum of the vertical direction would be n pushing up minus the weight pushing down has to come up to 0. And that's why you guys who saw it already said, yeah, this normal force is just going to be the simple case where it's just the weight of the object. So this then would be the coefficient of friction times the little m plus the big M times g times the distance it traveled. So there's my Q2. And so if I put that into here, I get half little m plus big M big V squared equals coefficient of friction little m plus big M times g times distance traveled. And so big V when I bring the 2 over to here, is 2 times the coefficient times g times distance traveled times the square root. And so there's my first calculation using, at this point, only conservation of energy. I haven't got to the momentum part. But if I put in those numbers, 2 times 0.65 for the coefficient, 9.8 for g, and 7.5 for the distance it slides, and then take the square root of that, and it looks like I got a 9.77 meters per second is the speed after the collision. So knowing that, and then coming back to this equation, the speed before the impact would be m plus big M over little m times the speed after the impact. So the little m was 12 grams, which I'll convert into kilograms, although I don't think it's necessary for this one. And then the big mass is 0.1. Divide that by the little mass, and then multiply it by this speed of 9.77, and sure enough, I should get the speed. So the top one is 0.112 divided by 0.012. And then times the speed I had before, looks like about an 87 meters per second. Those are some big numbers. Did I do this right?
I got 2, but I was worried that I did it wrong, but then you got the same answer.
Yeah, okay, so you guys got the same number. And I guess it's because 7.5 meters is a long way to slide. And that's a lot of friction, 0.65. So maybe these numbers are big, but that, 87 is almost 200 miles an hour here. So I'm going to shoot it out of a little can here. So this wasn't just thrown by a human. This has a good speed. This is, somebody took some plumbing, some clay, some some hairspray and a match, boom, and there goes the wad of clay here. Nah. All right. So anyway, so those are the maybe overly realistic numbers here.
How fast is that, you said?
191 miles an hour. So.
I'd like to watch that.
But it is a small amount of clay, though. I mean, this is not that much clay. I mean, just a little. Isn't a penny's what, 3 grams ish? So this is 4 pennies worth of clay here. So still going pretty fast. Well, anyways, whether they're realistic numbers or not, hopefully, and I'm glad to hear you got the same ones, because when I don't get realistic numbers, I get concerned that I did something wrong, because usually they give pretty good realistic numbers here, unless they're trying to, make you see something else. Then in this case, there's probably something more complicated going on here. It would be a little premature because we haven't gotten to rotations. But depending on where you hit this, if you hit it in the high corner like I've illustrated, above its center of mass, this is probably going to make it tumble and rotate. So that's what we got to talk about. This, you're going to hit it that hard, you better hit it right at its center of mass there and keep it from tumbling here and just push it on straight through. Well, let me do another couple of examples here, and then we'll move on. 27 is the next one. And I grabbed this one because it's a 2-dimensional. You've noticed so far that I've done all 1-dimensional collisions and had different reasons for picking those problems. But 27 is this billiards game or pool. It says here, a billiard ball is moving at 5 meters per second. It strikes a stationary ball of the same mass. After the collision, the first ball moves at a speed of 4.33 meters per second at an angle of 30 degrees with respect to its original line of motion. Assuming an elastic collision, ooh, key word there, right? No heat, okay. Assuming an elastic collision, and I'm glad they add this, and don't worry about the rotation or the friction of the felt, okay. Find the struck ball's velocity after the collision. All right, so here's the picture. The picture is we've got one object of mass m. They don't tell us, but they do tell us it has a speed of 5 meters per second. And it's coming along, and then it strikes a second one. The first one ricochets off, and so instead of going in the same direction, it now is at 30 degrees. And they say it has slowed down a little bit to 4.33 meters per second. Strikes a stationary ball. After the collision, the first ball moves at 4.33 at an angle of 30 degrees with respect to its original line of motion. Assuming the collision is elastic, find the struck ball's velocity. So this second ball would be heading at some angle theta with some velocity, I'll just call it v, unknown. And that's what we're after. What is that velocity? All right. How am I going to solve this? Is energy conserved? Yeah, energy is always conserved. I'll even go one better. Is kinetic energy conserved? Right, it is. Right? And we can write that one out. Oh, why don't I do that first? I don't even think we'll need it, but I'm going to write that one equation out. And so I would start off by saying, okay, 1/2 m5 squared equals. See, that would be the kinetic energy before the collision. What does it equal? Well, 1/2 m 4.33 squared plus 1/2 m v squared. Oh, actually, I guess that's all I need. Bummer. I wanted to do more than that. So I'll tell you what, I'll expand the problem. Because that doesn't even have momentum in it. But let's answer the question is, what is its speed and what is its angle? How's that? Okay. So what is its speed can be answered right there. The fact that they said it's elastic means all the kinetic energy is the same here. And fortunately, even though they didn't give me the m, they're all the same. They can cancel off, and I could even cancel off a 1/2 from every term. But what that would mean then here is a 5 squared minus a 4.33 squared, taking the square root of that would be the speed. So I wonder if the author meant for it to be quite that simple. And that's 2.5. It's hard to believe. Is this a blue problem or a black problem? It is a blue problem, and I'm not sure why. All right, but I think when we add the next part, what is the angle, then it elevates it to a blue problem. It says, okay, what is the angle here involved? So there's the first step, that we do have conservation of energy, and more than that, we have conservation of kinetic energy, because I said that word elastic. But what I wanted to show by this problem was also conservation of momentum, and then have the x and the y conserved. And I wanted to write out both equations. I wanted a two-dimensional collision. Okay. So when I write out a two-dimensional collision here, I might grab a coordinate system that looks something like this, and so this is the x direction and this is the y direction, I would say, all right, my initial momentum in the x direction has to equal my final momentum in the x direction. And my second equation is that the initial momentum in the y direction has to equal the final momentum in the y direction. And so that's what I was trying to say an hour ago at the beginning of class here, that, you know, in a two-dimensional world or in a three-dimensional world, we would have x, y, and z that have to be conserved. So not only do we have the momentum, the components of the momentum, but we also have the scalar quantity, the energy. So if I put this in over here and I look at this, I would say I have mass times the velocity in the x direction. So there's my m and my 5 for the momentum of this first one. And the second one's stationary, so this is the momentum initially in the x direction. What does it have to equal? Well, I guess it has to equal to an m, a 4.33, and then a cosine of 30 degrees. That would be my momentum and the x component. And that's what I wanted you to see. See how I got the momentum is still mv, but the x component would be the adjacent piece to the 30 degrees. And then the second object would be an mv, and then it would be cosine of theta. Now looking at this one again, the m's would cancel off. And if you'd already done this step here, knowing what the v is, then you only have the unknown theta, and we can solve this for theta. And I will in a second, but let's write out this one too. What is the momentum in the y direction? Well, before the collision, it's 0, right? Neither one is moving in the vertical direction. The first one is moving only horizontal. The second one's not even moving at all. So the initial momentum in the y direction is 0. That's why when they collide, did you notice how one I drew going up and one going down? How did I know one has to go up and one has to go down? That's the only way you're going to get 0 momentum in the vertical direction after the collision. They both couldn't go up. They both couldn't go down, because I got to get this to come out to be 0. And so I know one's going to go up and one's going to go down. And so that's conserving momentum in the y direction. So the one that goes up, yeah.
Those ones cancel out.
Oh, well, it would be, I'm dividing both sides of the equation by m.
Are they both the same mass? Or?
Oh yeah, yeah. Somewhere in here they said it strikes a stationary ball of the same mass. Yeah. So, and the same thing happened back here. This second one had the same mass as the first one. So this was the first one and that's the second one. So I'd even call them 1 and 2 because it said the same. All right, so then the momentum in the vertical direction for this guy would be m 4.33 meters per second sine of 30 degrees. And the other one would be mv sine of theta, but in the negative direction. Did you catch that? So there's the magnitude, there's the component, and there's the direction, as we've done so many times for vectors. Magnitude, component, direction. And so again, if I already had done this one for v, I should be able to find theta here too. So you might even say that they gave me too much information here, because there's only 2 unknowns. One is the angle and one is the velocity, and yet I have 3 equations, here, here, and here. So I only need 2 of these equations in order to solve it. It probably would have been a more interesting equation had they given me, you know, maybe they didn't give me that angle. So they gave me, you know, there's 3 unknowns in my 3 equations. But that's what I wanted to set up. I wanted to set up all 3 equations. So this is one equation. This is another equation. And this is another equation. And I kind of suspect, maybe I'm just guessing because this is kind of what I saw. If you look at momentum, here's your 2 equations, 2 unknowns. And so that's kind of where I was going with this. I wanted to write out the equation for momentum in the x direction, the equation for momentum in the y direction, and then solve it. That's why, if you recall, when I started this, I said, we probably don't even need this one, but I'll write it out. And then once I wrote it out, I said, well, wait a minute, this is the easiest way to do it. It's only got 1 unknown in it. All right, but let's see if these other ones work out just the same here. So if I solve this for theta, I guess this becomes 5 equals to 4.33 cosine of 30 degrees plus 2.5 times cosine of theta. And got a little bit of algebra to do here to come up with cosine of theta. But it should be 5 minus 4.33 times cosine of 30 degrees. Then if I divide that by 2.5, I get 0.5, which then means if I take the arc cosine of that, I get an angle of 60 degrees. So this says, whoops, 60 degrees. I didn't mean to write 90, but I might as well say it. I was thinking 90 because something that you may not realize if you haven't gone through the math. I don't even think the author mentions it, but if you have one object moving and you strike a stationary of the same mass, okay, so it's got to be those conditions. It's got to be a stationary object. It's got to be the same mass. But if you do, the two will go off at 90 degrees to each other. And if there's no rotation. So not really true for the game of billiards, but shuffleboard. One's sitting there, the other one's hitting, they'll ricochet off at 90 degrees. Guarantee it. And so there's our 90 degrees. Or if you do like the game of billiards, I mean, you can get rid of the rotation by hitting the ball either dead center and it slides for a while. You know, if you're going a long distance, it begins to roll. But when you first hit it right at the center, the ball is going across without rolling. And so if you know you want this ball to go into that corner pocket and you want this one, the cue ball, to go off at 90 degrees, I used to watch these guys play pool, and they'd always hold their hand out like this over the, okay, here's the ball they want to strike, and they kind of do that. And so there's the ball in the pocket, there's the cue ball, you know, kind of close to a 90 degrees, and so they could do it, and they do it. Now, as long as I'm mentioning it, if it's rolling, then the ricochet is, regardless of what angle this is, and this one gets close to 30 degrees. And I say close, but it's somewhere, you know, between 20 and 40, depending on how fast it's rolling. But then they would do this kind of thing. Oh, hey, here's 30 degrees. So they go, okay, I'm going to make it roll, and I'm going to have the ball going in this direction. I'll make that one. And where's the cue ball going to go? Okay, I want it to go that way. So they can kind of line up their next shot there. So, yeah, so. Yeah, so there's your little extra money for the weekend there, right? Play little games of billiards there. So, anyways, that's why the 90 came in. But it doesn't surprise me then that it comes out to be 60. In fact, I would have been very surprised if I didn't get 60, because I knew that fact. Also, the same thing can be done here. If I go through this math, again, not knowing the m's, but they would cancel off. Hopefully I will get the same number here. So if I put a 2.5 here and I work through the math, hopefully also that will give me the 60 degrees. And so let's see if it does. 4.33 times the sine of 30 degrees, so that's this one. I'll move this to the other side, so now it's positive. Then I will divide it by 2.5. Then I will take the inverse sine of that, and good. That one comes out to be 60 degrees too. So obviously by that point you wouldn't have to do it, because 2 equations is all you need for the 2 unknowns. And so we use that equation and we use that equation. We're good, but nice confirmation, if you will, on the fact that there's the next speed of it. Well, let's try another 2-dimensional one that maybe is a little more complicated, where they don't have the same mass and they're not stationary. But hopefully you'll see it's the same basic principle. In fact, maybe it's worth saying again. I'm hopefully getting across to you as we get into each chapter. Do you want the answers to all the homework problems in this chapter? All right, here it is. Initial momentum is equal to final momentum. There it is. As long as there's no external forces. Don't forget to throw in things like conservation of energy, coefficient of friction, free body diagrams, kinetic energy, blah, 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 blah. Yeah, and then work out the details. Okay? But again, it's that same principle that I just can't resist. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. So the actual amount of information that you memorize in this class is probably the smallest amount of any class you've ever had, or at least any college class. I mean, since kindergarten, you've probably learned more in kindergarten in terms of memorization, the counting to 100 and the letters in the alphabet than you are this semester. But it's the deductive reasoning, paying attention to the details, deciding what to do, which is the hard stuff. And so when you see it in that light, then hopefully it makes it a little easier, not harder. Yeah. What?
I got 91.2. So I just assumed because it was pretty close, it was rounding.
Oh, yeah, okay. Yeah, good question. Did you get 977 here?
Yeah, if you just punch the same numbers in on top there, you should get 91.2 instead.
Huh. Well, then I'm going to try it here. Point, so the numerator would be 112, and the denominator would be 0.012. So I'll take that quotient. And then 9.77 is, 91. I don't know how I got that. Maybe it was a fat finger mistake. So, yeah, and sometimes I need a bigger keyboard there. So, yeah, good. All right, so anyways, back to the example problems. But, you know, as much as I like joking with you and telling you, I'm dead serious. That's the idea. And hopefully you're seeing as I do this example. It's just the same principle again and again and again and again. Now, the scenarios are different. You know, sometimes it's a 2-dimensional problem. Sometimes it's a 1-dimensional problem. Sometimes one object is moving, the other's not. Sometimes both are moving. And you'll see that here in this one. Number, what'd I say, 27 we just did. So 34. Number 34, it's that same idea here of like we just did here in 27. It says here that the mass of a blue puck is 20% greater than the mass of a green puck. All right, so we got 2 pucks. They come in for a head-on collision. Before colliding, the pucks are approaching each other with a momenta of equal in magnitude but opposite in direction. And then the green puck has an initial speed of 10 meters per second. Find the speed of each puck after the collision if half of the kinetic energy of the system becomes heat in the collision. Okay? And they even give a little picture down here. It looks something like this. They've got one side over here that is a green puck, and another side which is a blue puck. And so here's the blue one going this way. Here's the green one going this way. They come together and hit so that they ricochet off. And I think they give some angles here in the picture. Well, it looks like 30 degrees for each of them. So this one goes off at 30 degrees from its original direction. This one heads off at 30 degrees from its original direction. Okay? And so let me read it again here. The mass of the blue puck is 20% greater than the mass of the green one. All right, so why don't I call the green one M? So the blue one would be, 1.2 M, right? 20% greater. Okay, so that's what that first said. The mass of the blue one is 20% greater than the mass of the green one. Before the collisions, the pucks approach each other with a momentum of equal in magnitude, but opposite in direction. Now, I'll stop there, because that statement is saying, and so if I put V1 for the green and V2 for the blue, I guess what we're saying is MV1 must equal 1.2 M V2. Crossing off the M's, and V1, which is the green one, must be a little bit bigger than the blue one by 20%. That's how they end up with the same momentum. So one has more mass by 20%, the other one has more speed by 20%. And so that's kind of what that first statement is saying. All right, fair enough. So the momentum is equal in magnitude in opposite directions. The green puck has an initial speed of 10. All right, so if I put a 10 in here for the green one, then that means this second one, this blue one, is 10 divided by 1.2, or 8.33. 8.33 meters per second. And maybe I'll even put that in my diagram. So this is 8.3 meters per second, whereas this one over here is 10 meters per second. Okay? So there's that second sentence. It says, find the speed of each puck after the collision. If half of the kinetic energy of the system becomes heat in the collision. All right, so this is the given information. And actually we did a little bit of work then to find the speeds also. But after the collision, I would have something like this. And I guess I would ask, do I have conservation of energy? Yes. Do I have conservation of momentum? Yeah, I guess if we look at the two together, I mean the two have a force on each other. They don't really say frictionless, do they? But they say the pucks come together before colliding, da-da-da. Yeah, they should have made it more clear. But I think they're trying to imply here that they're on a frictionless surface here and they're sliding along and they're ricocheting off. So then I would have my three equations. I would have initial momentum in the x direction is equal to final momentum in the x direction. And initial momentum in the y direction is equal to final momentum in the y direction. And so there's the momentum pieces of this chapter. But also the energy part of it comes into play. when I say the kinetic energy initial is, I guess, equal to twice the kinetic energy final. Can I write it that way? Instead of writing final plus heat, because then they say half of it goes into heat. So that means half of the final kinetic is left over there. So these are the three pieces of information. Let's write them out and see if we need all of them and see how they're useful. And so in the x direction, I guess I would say 0 initially, right? I mean, isn't that the whole purpose of their discussion here? It's how we got the different speeds, is they said that one would have a momentum and the other one would have a momentum, and so the momenta total is 0. And so if we label this as, I'll put it in blue, but if I label this as V final number 2, and I label this as V final number 1, what you're saying here about the green one is that its mass times its final speed times the cosine of 30 degrees is how much momentum the green one has. But the blue one then would have a minus, because it's going in the negative x direction. Its mass is 1.2 m. Let's see, its final speed is going to be V final number 2, and it would be cosine of 30 degrees. And did I get it right? That's its mass, that's its speed, that's its angle, that's its mass, that's its speed, that's its angle. And so that would be my first equation, and it looks like it works out kind of nice in the sense that the m's would cancel off. Even the cosine of 30 degrees is the same here. And as I move this to the other side of the equation, 1.2 times the final speed of number 2 is equal to the final speed of number 1. And it doesn't really surprise me, but that's what this statement said here before the collision. So obviously to have it before and after, they're kind of saying the same thing in terms of their speed, because they have the same angle in this case. They have the same ratio of the masses, so they must have the same ratio of their speed. So that's my first equation. My second equation is in the vertical direction. And the vertical direction, I guess, how much momentum do I have in the vertical direction before the collision? Well, 0. They're coming straight in, so they only have x's. And then a ricochet up. And so the green one has a mass of m and a final speed of number 1 and a sine of 30 degrees. I don't think this one's going to give me any more information, but let's see here. Whereas the blue one would be 1.2 times m, so there's its mass. Its speed is V final number 2. Its angle is also 30 degrees, so sine of 30, and it's headed down. But I think this just tells us the same piece of information as the x component. Yeah, it should. And so we just get 1.2 times the final speed of number 2 is the final speed of number 1. So whether we look at the momentum in the x or the momentum of the y, in this case, one is going to give us the same information as the other. But again, going back to what I was saying, that's what this whole idea of the general principle says. Write it out. Just say the momentum of the x before and after are equal. The momentum in the y before and after are equal. Just write it out. See what it gives you. And then also write out the energies. See what it gives you. So it looks like in order to finish this problem, I'm going to have to make sure I look at the energy too. So as I look at the energy, I would have, and I'll start with the green one over there, 1/2 times m times its speed of 10 squared. And the other, the blue one, 1/2 of 1.2 m times its speed. What was the speed before? 8.33 squared. So that is the total energy before the collision. That has to equal twice the energy after the collision. So after the collision, it is 1/2 times the green one, which would be a final speed of number 1 squared, and the blue one, which is 1.2 m, and final speed of number 2 squared. And so this looks like I will have a V1 and a V2. Together with this V1 and V2 means I've got 2 equations and 2 unknowns, and I can solve that. Let's see. It looks like every term has an m in it again. So that's why they got away at the beginning by not telling you the mass of the green one and then telling you the blue one was just 20% more. For that matter, it looks like there's a 1/2 in everything too. So I'll get rid of the 1/2, although I was kind of tempted to multiply by that 2 to get rid of the 1/2, but I like it, get rid of it on that side. So this side of the equation, if I grab my calculator here, would be, let's see what's left over here. That's 10 squared, that's 100. Add to it 1.2 times 8.33 squared equals, and at this point I have 183 on that side of the equation. And then over here, I guess I have, actually I'm going to bring the 2 over to there. How's that? 2. And then I have V1 squared plus 1.2 V final 2 squared. And that's where then this one can come in. I'll put V1 here. And so 183 divided by 2. And in place of V1, I will put 1.2 times V final 2 squared. And, oh, and it's the whole thing squared. Be careful there. 1.2 V final 2 squared. And so V final 2 squared is my like term. So it looks like I've got a 1.2 squared, and then add to that a 1.2 and 2.64. So 2.64. So a little more arithmetic here. This side of the equation is 183 divided by 2 here. Then I'll divide that by the 2.64, take the square root of all of that, and if I've done my math right, 5.89 is the speed of number 2, which means then the speed of number 1 is 1.2 times number 2, so 7.06, so 7.06. Ta-da! And so again, just start at the fundamentals. Start with the idea that momentum is conserved and write it out. Write out the energies. And now you solve the problem. And it could be pretty long problems with the algebras because you got squares in there and square roots.
How'd you go from the velocity final 1 squared to 1.2 velocity final 2 squared?
Oh, here? I use this. So putting that for velocity 1 from that step, yeah. All right, well, let's see. I got a couple more listed here. Let's see if they would be enlightening or, oh, actually they would be. Well, why not? We'll do that, and maybe we'll still get a chance to talk about the other half of the chapter, or maybe that'll just wait till Monday here. But 57 is a nice review one, and the other one, 65, is a really good review one. Again, just one of these sets of problems that just especially 65, just pay attention to the details here of what they're asking, what is going on, and a good physical picture would help here. But 57 is kind of listed as a review one. It has some of the properties of this particular chapter, but then it goes back a few chapters too, and so that's why I picked it here. It says this, that a bullet of mass little m is fired into a block of mass capital M, which is initially at rest at the edge of a frictionless table of height h, as shown in the figure. So the picture looks something like this. Here's the table. This block of mass capital M is then fired with a bullet of mass little m. By the way, maybe it's clear here, but it's worth repeating. I said it once before. Because you got to make these decisions, particularly on the final exam, where by the time we get to the final, we've learned so many principles. Newton's laws of motion, conservation of momentum, conservation of energy, conservation of angular momentum. I mean, hopefully you're seeing that if you have a collision, two things interacting, what principle are you going to use? It's momentum. That's the one thing we know. Whether they stick together and it's perfectly inelastic, whether there's heat and so it's elastic, or there's no heat, it's elastic, doesn't matter. The momentum is conserved. And so that's an important piece to know. And so every time you have an interaction, think about that. What am I going to do? It's like I told you in the last unit. If you have a question asking for speed and they give you distance, think in terms of energy. Don't think in terms of acceleration or forces. But if the problem asks for acceleration, or if the problem asks for tension in the string or something, then think about Newton's laws, think about forces, think about the acceleration. And so knowing the advantages and disadvantages and making that decision which way you're going to approach this really can help. And so here is a bunch of collisions, and this happens to be another bullet. It's a violent discipline. There's a lot of bullets hitting other bullets here. So if it's any consolation, it's a lot less than it used to be when I was a student. I think like every problem was a bullet, and I know there's been a big push to make sure that they've been taking these rifle ones out. So I guess they've taken guns out of school too. I remember we used to have a shooting range down below the gym, and so you'd go down in the gym, and that was part of your PE class. And I suspect you guys don't have that for your PE anymore. Yeah, you have to load the .22, and you have to learn to fire. Everybody's got to learn how to fire a gun, and so it's just a different world. And actually, now that I'm a teacher, I'm kind of glad that guns aren't allowed in school, to be quite honest, especially when I pass back a test like that last one there. So, yeah, it's like, okay. Can I imagine? Here's your test. Let's go in lab. Grab a gun. I just wouldn't feel comfortable with that. LA County. San Dimas, if you're familiar with eastern LA County. Yeah. So, just old, bald, old, fat, Good thing I'm married, okay, type thing. Actually, that was even kind of rare then, I got to admit. I started school in 1980, high school in 1980. And most of them were done. But in the 60s, and particularly in the 50s, that was just required. I think even an ROTC was required by all male students, I think, in the 50s. That was a change too. Well, anyways, I'm not that old, so I don't know exactly what happened there in the 50s. I'll have to ask my dad. But back to this problem here. So here's the impact, and what they're saying here is this is some height h here, and the bullet comes along, and hopefully you're seeing this idea that obviously using the momentum is going to make the collision, and then once it makes the collision, that's going to give me my speed. Once I know the speed, then I can go back to the old stuff we learned back in chapters 1 through 4 and figure out then this question, which is D, how far did the object travel before it hit the ground? And so let me read the problem now that I got kind of sidetracked there on a little story here. It says, but a bullet of mass little m and a block of mass capital M initially at rest at the edge of a frictionless table of height h. The bullet remains in the block. Now that's important. What does that tell you? Perfectly inelastic, and now the bullet and the block are going at the same speed. So basically, it gives us a way to find out its momentum and find its speed after the impact. That's why that's an important piece. The block then lands a distance h from the bottom of the table. Oh, here's the question. Determine the initial speed of the bullet. And so if you shoot this block and it lands d, so you get the ruler out and you measure a distance d, then you should be able to find this v, what's its speed. Which, by the way, although I was joking about the bullets firing into it, we have next week one very similar to this. You saw it in 102. It's a little, we call it the spring cannon. It's a little round plastic ball that you pushed into a spring, and you push on the spring, and it shoots the plastic ball out. And so we're gonna shoot our plastic ball. Now, it won't be going fast enough to penetrate into a piece of wood, but what it will do is it will be hooked on a pendulum, and it will go into a little cup. It'll catch it and swing up. And so instead of getting the impact speed by seeing how far did it travel, we will get the impact speed by seeing how far it swings up. And so it's a good conservation of momentum problem. And like I said, you'll see that next Monday when we do the lab, when we shoot our cannon. But here's what you're looking for, v. Now again, applying our principles from this chapter and writing it out, I should be able to do conservation of momentum. Or maybe I should ask, is momentum conserved? When is momentum conserved again? No external forces. So any external forces? Well, certainly once it hits the ground, there's external. How about when it's flying through the air? Force of gravity, right? So I would say momentum's not conserved as it's flying through the air either. But can't we do what we did a couple problems ago? What about immediately after the impact? Not a chance for any friction or any gravitational to pull on it. So what we could do is we could say this, that the little m times the little v would be equal to the little m plus the capital M times the capital V. And what I mean by capital V then is what is the velocity right after the impact. And so I could apply conservation of momentum, but it's right after impact. After that, then the momentum begins to change. There is an external force on it. So I don't want to say that the speed down here is capital V. That's not what I'm saying. What I'm saying here is the speed right after the impact is capital V. And actually that's more useful, because if we go back to chapter 4 here, what did we learn about a projectile going through the air? Well, its vertical speed increased, but what about its horizontal? Yeah, it didn't change here, right? And so I'll keep this in mind, but I'll also go back to chapter 4 here and say, x equals to x initial plus initial velocity in the x direction times time plus 1/2 acceleration in the x direction times squared. And I'll put together with y equals y initial plus initial velocity in the y direction times time plus 1/2 acceleration in the y direction squared. And so those would be my equations, but of course only valid for constant acceleration. I don't want to forget that either. But I do have constant acceleration as it flies through the air, don't I? I mean, this is our projectile motion. So taking these equations and applying it to this as it is flying through the air, and taking my coordinate system, well, maybe I should ask, where do you want to put the coordinate system? Okay, I guess we did that a lot. We put the origin right where it gets launched. So if you did that, I would say the initial x position is 0, and the final position of where it lands is d. So there's the horizontal motion. The initial speed in the x direction is the capital V. There's the capital V that I'm going to use for my new stuff. And then multiplied by time. And then the acceleration in the x direction is 0. And so this breaks down to that. Capital V multiplied by time is my d. Which is why we did all these back in chapter 4, because we can use the vertical motion to get time, right? And so doing this and using the origin, as you said, my initial position is 0, then my final position is a negative h, right? It goes down h. And I'm calling down negative like we did back in chapter 4. Now we're much more sophisticated, so we could probably call that the positive direction if you want. Or should I just leave it at the negative? Or that's fine? Okay, half of you say one, half of you that. I'll just leave down as negative. So there's the negative distance. In fact, I hate to say it this way, but do you remember back to chapter 4? Oh, particularly chapter 1. It was a long time ago, but wasn't it kind of nice? How many kilograms are in 500 grams? That's a lot different. Oops. Excuse me. That's a lot different than the problems you just saw in the test and the problem you're seeing now. So we've come a long way. Although we got a long way to go too here. So they'll get harder here. All right, so continuing on here. Then this would be a 0 also, and which was kind of the key to the problem here, that you fire it and you have a speed of 0 in the vertical direction, and then you have a 1/2, and if we're sticking to that downward as a negative sign, I'm going to put a negative 9.8 and go t squared. And that's why the negatives show up on each side. And so had we called down positive, of course, we would have just started with that equation. But there is the equation for time. And now we can put it together. We can put our old stuff from chapter 4 together with our new stuff here from chapter 9 and get this speed. So I'll start over here by solving this for time. So that means h divided by 4.9, take the square root, that's t. Knowing that and putting it into here means d equals to this capital V times the square root of h over 4.9. Then taking this one and saying V equals little m plus big M over little m times capital V, then I can take this stuff that I just did from the old chapters, and let's see, that would be d divided by the square root of h over 4.9. And maybe simplifying the compound fraction so that this becomes the square root of 4.9 over h, and then times d, I get the little formula that then, okay, if you measure h and you measure d and you measure the masses, you should be able to calculate then what the v is, what's the velocity. And like I said, you do one very similar to this in the lab next week. You measure some things, heights and angles and masses, and then you figure out what is the speed of this little cannonball that you fired. Uh-oh, maybe I didn't save myself enough time to do one more. But let's throw it out there. Because again, it's just kind of a nice problem, particularly the part A where it does momentum. The other parts are maybe not really a momentum one, but still kind of an interesting problem. But number 65 says this, and it says review problem also. And it's going to make you go back to chapter 4 instead of this chapter 5 for this one. That one.
Problem when you divide that small sides, wouldn't it have to go under the big V as well?
Wait, what?
When you
Oh, here?
yeah.
Well, when you divide, so I'm dividing both sides by m.
Oh, okay.
And yeah, so this is the same thing. You can either multiply them first and then divide, or you can divide them first and then they multiply. So it's the same thing. And I guess I just chose this so that it would be grouped, the masses would be grouped together. So what does 65 say? It says a light spring of spring constant 3.85 newtons per meter is compressed by 8 centimeters. There they did it again. 8 centimeters. Not going to fall for that. And held between a 0.25 kilogram block on the left and a 0.5 kilogram block on the right. Okay, so 0.25 on the left, 0.5 on the right, a spring between them with a spring constant of 3.85, and you compress it 8 centimeters, which I'll write as 0.08 meters. So 2 weights, spring in the middle, push them together. A light spring of spring constant 3.85 is compressed 8 centimeters. It is held between a 0.5 kilogram block on the left and a 0.5 kilogram on the right. Both blocks are at rest on a horizontal surface. The blocks are then released simultaneously so that the spring tends to push them apart. Find the maximum speed of each block if the coefficient of friction between the surface is A, 0, B, 0.1, C, 0.462. Okay? So the first case, A, the coefficient of friction is 0. So it's a frictionless surface. First question then. If we look at the 2 blocks together with the spring, is this a conservation of momentum problem? Right? They're just pushing on each other. So as they go shooting out, I would say that the initial momentum in the x direction is equal to the final momentum of the x direction. Now before I release them, that's easy to figure out their momentum. Isn't it? Before I release them, their momentum 0. And so then this one goes shooting out, which I will call velocity v1, and this one goes shooting out the other direction, which I'll call velocity v2. And so what I would have is a 0.25 for the mass and a v1, but that would be a negative direction. And the other one would be 0.5 v2, and that would be in the positive direction. And so as I solve the math here, and I move this to the other side and then divide by the 0.25, I guess I get this for my mathematics, is that, hey, these guys are going to have a speed related by a factor of 2 to 1. Makes sense, isn't their mass 2 to 1? So their speed should be 2 to 1. The heavier one should have a smaller speed, and the lighter one should have a bigger speed at twice that.
Where does X come into that drawing?
That's how much the spring has been compressed. So the spring started out like this, and then it's pushed in 8 centimeters, and then held. And then you let go of it. So that's what I was saying earlier, that step A is really a conservation of momentum. But wait a minute, what about conservation of energy? Is that true? Yeah. So the second part of this is 1/2 kx squared would have to equal 1/2 0.25 v1 squared and 1/2 0.5 times v2 squared. And so what you're saying here is that this is the kinetic energy after the spring has been released. It came from the spring itself. And so that would be one equation. That would be a second equation. Two equations, two unknowns. And maybe that's as far as we're going to get today. B and C aren't so much about conserving momentum as much as they are about not conserving momentum because you have a frictional force. So maybe I'll just leave that and we'll run out of time and ask this. In part B and C, when there's some friction, can you use conservation of momentum? No. But you could still hopefully answer the question, what is its maximum speed? Because couldn't you figure out that the energy from the spring then goes into kinetic and heat as they move apart? And the only trickier part is to figure out how much each one moves. So I'll stop there. But there's your two equations, two unknowns.